Welcome to my talk. My name is Ramsey Makan, and today I'm going to be discussing Ramsey theory, or an introduction to it, and Ramsey numbers, and Ramsey's theorem, none of which is actually mine, but I'll explain all of that in a little bit. Oh, nice. Okay. All right, let's begin with a quote from Paul Erdős, one of the most famous mathematicians of the 20th century. And he has his name over tons and hundreds of papers. And this quote attributed to him begins with, "Suppose an alien force vastly more powerful than us landed on Earth demanding to know the value of R5, or else they would destroy our planet." You might be wondering what R5 is, and I'll get to that. In that case, I believe that we should marshal all our computers and all our mathematicians in an attempt to find that value. Again, there's more to this quote, which I'll get to as the presentation goes on. But the main question that we have is, what is R5? So let's begin with a situation, friends, strangers, and R of 3. Suppose that we're at a party, and every pair of people at the party is either friends or strangers. There's no in between, and if you know somebody, you're BFFs with them, right? The question is, how many people must there be at this party to guarantee that there exist either 3 mutual friends, like a triangle of 3 people that are all friends, or 3 mutual strangers, the same triangle in the other case. And so the question is, how many people do we need? Well, this is actually a mathematical question because we can represent each person with a vertex, and we can represent each relationship with an edge. So if I click escape here, I'm going to draw on the window now. So as we can see, we're going to have vertices that are labeled. We're just going to use letters to represent different people, but abbreviating them by their initials. And we're going to color the edges blue if the people know each other and they're friends, or red if they're strangers. And these are edges connecting vertices, right? So let's begin with the case of 3 people at this party, A, B, and C. We pick blue and we say, okay, how can we color this so that there is not a triangle of all blue or all red? Well, it's very easy in the 3 case because you can make a triangle like this with one edge that is lacking. So having 3 people is not sufficient to make a group of 3, right? What about in the case of 4? We're going to have people A, B, C, and D. And we're going to color the relationships between them again. So this time, I'm going to make every person like this friends, but the 2 diagonals, which I need to show the relationship between A and C and B and D, I'm going to make them strangers. Now, as you might see, there is no red triangle, there is also no blue triangle. So having 4 people isn't enough to guarantee that I have a click or a complete little triangle that is all red or all blue. What about 5? You might think, okay, certainly 5 is enough, right? Well, let's draw our people out. And we'll use blue to represent friendship. I'm again going to draw kind of a symmetric pattern. And again, you might not know what this pattern should be going in, but if you were to experiment a little bit, you might come to this conclusion. And now I'm also going to draw the relationship between any 2 non-adjacent people to be enemies, making like a star. And guess what? There is still no red triangle or blue triangle, meaning that 5 people isn't even enough to guarantee that we have 3 people that are mutual friends or strangers. And there you go. There's the exact same image, just enhanced and formatted a bit better with opposite colors. So 3, 4, and 5 people is not good enough. Okay, scroll. But 6 people will work. And so here's the proof that R of 3, I'll say what that is in a sec, is equal to 6. And the theorem is that in any group of 6 people, with everybody being friends or strangers, there exists 3 mutual friends or 3 mutual strangers. And we can actually do the proof visually before I show how you would write it out mathematically. Suppose we have person A, right? And we're gonna write the other people B, C, D, and E and F. These are our 6 people. And so A has 5 relationships with the 5 other people there, because there's 6 total. by the pigeonhole principle, it is necessary that of these 5 relationships, you have at least 3 that are red, or at least 3 that are blue, right? Because you have, A can either be all strangers with everyone, like 5, 4, or 3 strangers, or you can have 3 friends, 4 friends, or 5 friends, and that covers all of the cases. So, without loss of generality, tool in math to kind of just shorten the argument because everything is symmetric, we're going to assume that A has 2 strangers, or is strangers with 2 people, and is friends with 3 of them. And I'm just going to pick B, C, and D to represent them arbitrarily without loss of generality, however you want. So this is very close to showing that there must be a triangle that is blue or red. Because think about it this way. Let's focus on the relationships between the people B, C, and D. If any of them are friends with any of the others, what happens? I draw a blue edge, and then all of a sudden I get a triangle, ABC. It's blue. That means I now have a group of 3 people that are all friends. Or, similarly, if this edge was blue, or if this edge was blue, I'll just draw that, then I would also have a triangle ABD in this case. Now, in the other case, that's if any of the 3 edges between B, C, and D are blue. So what if they're all red? Well, as you might guess, then I would end up with this, this, and this. And then what is that? Another triangle. A little graph with B, C, and D with 3 red edges connecting them. This is guaranteeing that there's either a blue or a red triangle found in my graph of 6 people. And I only have to start with one person and look at their relationships. So again, the proof is that you label people as A, B, C, D, E, and F. By pigeonhole, that's the official definition of the pigeonhole principle. I'm basically fitting 5 relationships into 2 types. So one of those types has to have 3 of them, you know? Like 5 balls in 2 buckets, kind of. And then again, if any pair are friends, then those 2 plus A are 3 mutual friends. Otherwise, they're all 3 mutual strangers. So this shows that having 6 people is enough to guarantee this kind of relationship that I want. So, who is Ramsey? Or Frank Ramsey, that's his official name, and this is him. Now, I know what you're thinking. Are you not talking about Boston Celtics legend and NBA Hall of Famer Frank Ramsey, who played in the 1960s and won 7 championships, and whose jersey I actually have? But I grew out of that. That was in 2013. No, I'm not talking about him. He passed away in 2018. This Frank Ramsey was a British mathematician who was born in the very early 1900s and died at the very young age of 26. He studied and taught at the Cambridge University. What were his major accomplishments? Well, he made incredible contributions to a huge variety of fields, like combinatorics, which is what I'm talking about now. That's a field in math that's counting objects, essentially. Logic and philosophy, I have tests and sentences named after me, thanks to this guy. And economics, like Ramsey pricing. And as you see, Keynes-Ramsey rule, his advisor at Cambridge is John Maynard Keynes, who any economist should be familiar with. There's a whole Wikipedia article about that. So Ramsey theory, which is what my talk is about today, is a branch of combinatorics studying unavoidable order in large structures. Like how big must some structure be to guarantee that a particular property holds? Like in our case, we have a graph, and it got big enough to the point where there was some red or blue triangle within it, right? So let's define Ramsey numbers. The diagonal Ramsey number, R of k, is the smallest integer n, such that every 2 coloring of the edges of capital K sub n contains a monochromatic capital K sub k. And that's a lot at once, but that is really just an extension of what we were doing previously. So capital K sub n means a complete graph, like a mathematical graph in the sense of vertices and edges, of order n. So it's a graph with n vertices and an edge between every vertex. That's what the word complete means. It's because I need to say what the relationship is between all of the people, of the n people, right? And so in the graph capital K sub n, if n is large enough, then that would guarantee that I have a monochromatic capital K sub k, which is a smaller complete subgraph within that graph, such that everybody's connected via the same color, like they're all friends or they're all strangers. So we just found that R of 3 is 6 because 3, 4, and 5 weren't good enough, and 6, using the pigeonhole principle, we proved that it is. And this diagonal Ramsey number, it can be extended to be just non-diagonal Ramsey numbers. For example, it can have two arguments, s and t, which would represent the smallest integer that you need to color the, again, case of n. But this time, if you only needed a red case of s or a blue case of t, so s and t can be different. So I'm looking at the diagonal Ramsey numbers where k is the same for both, or s equals t equals k, and it is symmetric. So here's some examples. So the Ramsey number with inputs 3 and 4 is 9. And this is a graph showing case of 8. If I can't show you a graph in case of 9, that works because that's the first number where it fails. But this is the largest such graph where you can color all the edges such that there's no red case of 3, like a triangle, or a blue case of 4, which would be a square with the two diagonals. And this shows like a bound, right? This shows that R of 3, 4 has to be greater than 8. This monstrosity is a diagram, the Paley graph of order 17, which shows that the diagonal Ramsey number R of 4 has to be greater than 17 because this successfully does not have any case of 4s that are all red or all blue. Not that you guys can see that necessarily. And here's R of 4, 5, which is 25. And this graph is K sub 24, and it has no red case of 4 and no blue case of 5. Again, just showing a bound. And this number was only proved to be true in 1995, which is very recent. Here are some known values. If you look at this table with S being the row and T being the column, the diagonal entries represent the diagonal Ramsey numbers where S and T are the same. And so again, we were showing R3, that's R4. And you might notice R5 is a range. It's an interval, 43 to 46. We don't know it. It has been an open problem for over 70 years, and over many, many years, people have decreased this range between the two numbers. And I'll explain what that's about in a second. So let's talk about Ramsey's theorem. This was proved by his paper on a problem of formal logic in 1928. And this is essentially saying for any positive integers s and t, the Ramsey number R of s comma t exists. It's just trying to say that there is some n such that you get that sort of coloring pattern. Does it exist? Is there a bound that we can guarantee that this number is smaller than? And it's essentially saying that after a certain point, complete disorder is impossible. Like there will be some n such that we can take this, find this s or this t graph. And so there's a couple slides that I have to contribute to the proof of it. So some base cases, R of s comma 1 equals 1 for all s, because if you need to get a red case of 1, that's just a point, and so that's guaranteed to be contained in any one point, so all you need is 1. And R of s comma 2 is s, the argument is there. Basically, if we have s vertices and we're looking at the graph case of s, and all of their connections are red, then we have a red case of s. But if any one of them becomes blue, then we have a blue case of 2, which means that that's enough to get R of s comma 2, right? In computer science, we're kind of like, this is an analogy, essentially. We're trying to build the base cases, and we're going to be looking at the bounded relationship, which is an inequality that we need these base cases to refer back to. So here's a lemma. R of s comma t is less than or equal to R of s minus 1 comma t plus R of s comma t minus 1. This was proved in 1955 by those two mathematicians. And there's 4 steps to this proof, which I'll go through a tiny bit quickly. So if we let n be the sum on the right side, then we can take any two coloring of k sub n and pick any vertex v, right? So we're looking at the complete graph with n vertices, and we picked one vertex v. And so there's n minus 1 other vertices. So if we consider all of the other vertices that are connected to v via either a blue line or a red line, and we let m be the set of all the blue neighbors, it's a set of vertices, and n be the set of all the red neighbors, then we can, by pigeonhole, say the following. We know that the size of m and n added together is equal to n minus 1, right? So that allows us to say that the order of m plus the order of n plus 1 equals this sum by what n was equal to. So this means that either m contains at least that Ramsey number of vertices, or n contains at least that other Ramsey number of vertices. And again, to reiterate, this is kind of bounding R of s comma t, if we remember that table, by the value above and to the left of it. If if we add those, that would be strictly greater than or equal to R of S comma T. So anyway, oh, I do have this. Ramsey theory in many contexts is just a huge generalization of the pigeonhole principle. It's about finding patterns, because if you make your sample size large enough, you're guaranteed to get something. So anyway, there are two similar cases here that basically show that based on the way that we constructed M and N, the subgraph on M will contain either a red case of S or a blue case of T minus 1 because it's greater than or equal to that Ramsey number. But if V is connected via a blue edge to every vertex, then you include V and you attach it to all the vertices in your case of T minus 1, and you get a blue case of T. So you have either a blue case of T or a red case of S. And the exact kind of opposite symmetric argument for this one. And all of this is really to prove, again, this lemma, which I can explain more again later, but I want to go faster. So you can also prove this bound if you didn't like the other one because it is involving other Ramsey numbers, and you want just a combinatorial upper bound. This is a binomial. This is a base case, and then this is the inductive step where we use what we just proved, that lemma. Then we are using induction to assume that the statement holds for those values. And then right here, we use Pascal's rule, which is a rule in combinatorics to add two binomials. And you get exactly what you needed. So there you go, statement holds, and there's an upper bound. So let's look at the history of the bounds with Ramsey numbers. Erdos, who I mentioned at the beginning, combined an upper bound and a lower bound to give us this first estimate. We know that the diagonal Ramsey number R of k is somewhere between square root of 2 to the k and 4 to the k. And these are both powers of 2. You can rewrite them right as 2 to the k divided by 2 and 2 to the 2 times k. So, well, the left one is a power of 2, k is not, but no. So the upper bound part follows directly from the combinatorial bound we just had. Like, if you plug in S equals T equals K to be the same, then this becomes this. And this is necessarily less than or equal to 4 to the K by the binomial theorem. If you want to expand that term on the left using the binomial theorem, you'll get that. And the lower bound was found by Erdos using a brand new method called the probabilistic method, where he essentially assigned probabilities to these sets and trying to represent the probability that some K set is monochromatic and seeing when that is less than 1. And if you think in terms of probabilities and use the union bound from probability, and you find that the probability that you have some sort of set like this is greater than 0 or less than 1, then you can prove your statement. And so this is a non-constructive technique that was, I believe, first used in this exact problem, and this is now used in many other contexts to solve different kinds of proofs. And so, a very famous approach from Erdos. So here's a history of improvements to Ramsey bounds. We have the top two that I already touched on, and over the past century, they've been improved. Most of these are the diagonal entries. In 2023, you can see we have the a S comma T, and that was the third to last row was the most important exponential improvement in 75 years. These mathematicians broke the barrier saying that R of k was less than or equal to 4 to the k by using an algorithmic construction based on book graphs, a specific type of graph in graph theory, to say that it's less than or equal to 4 minus this epsilon. And what is epsilon? Just 1 over 128. And that was good enough to be such a big deal that they went from 4 to the k to 3.9 ... to the k. It was a big accomplishment in combinatorics. So you can see where we're at now. These people in 2024 have improved it even further. And the numbers look very random. You have a divided by 50, a 0.14, but they have all these algorithms and papers in detail explaining how they got these. And I have some approaches listed on the right. So here's the table from earlier, even bigger. I only showed the top 5 rows and columns, but here's all the other values up to S and T equals 10. As you can see, as you go, we have no idea what most of these are, and the bounds are so wide that the 10th diagonal Ramsey number is somewhere between about 800 and 16,000, and nobody can say for sure where. And in order to actually verify the answer, we're going to need very, very robust checking algorithms that we don't really have yet. if we wanted to actually verify what R of 5 is, which we know is between 43 and 46 based on recent papers, we would need to check a number of graphs that is more than the number of atoms in the observable universe. So we're not really close yet. But different entries have been verified kind of recently since 2023. And you can see the entries with a star like 5.5, 5.6, and this one, which is either 40 or 41, have actually been improved in the past few years. So there's still a lot of work, and technically you could pick any one of these Ramsey numbers and just devote your life to shrinking the bound, and you would contribute something. So I'm just going to quickly touch on some extensions. You can use more than 2 colors if you're curious. If you wanted to color the graph in a way such as with 3 colors, you could do the following. The Ramsey number with 3, 3, 3 is 17. That means that if you use up to 16 vertices and make a complete graph, there's a way to color every edge with 3 colors such that there is no triangle that is all red, all green, or all blue. This is one of the 2 colorings that shows K sub 16 works, or it doesn't work, I guess. And also, those are the balance of 4, 5, and 6 colors trying to find triangles. Finite versus infinite Ramsey theory. There's an infinite Ramsey theorem saying that if you color the edges of the complete graph with the vertices representing the natural numbers, so like a countably infinite graph, then there exists an infinite monochromatic clique or complete subgraph within it. So like an infinite, we were talking about triangles and stuff that have the same color, but within a graph of infinite order, you can actually find an infinite subgraph that satisfies this. And this can be used to prove the finite version via a topological and compactness argument, interestingly. And another extension is arithmetic Ramsey theory, which I'll just kind of show here. But if you wanted to color the solutions to an equation, like Schur's equation, x plus y equals z, where the values can take on the inputs from 1 to n, and you were to color the numbers from 1 to n, then you can study how often are the solutions to that equation the same color, monochromatic. And this has, analogies with graph theory and combinatorics, and it's really all Ramsey theory, but it's arithmetic Ramsey theory. This is what I'm reading my paper on for the directed reading program, so I'll talk more about that from our presentation in April. And here's a summary. R of 3 equals 6. If we have a party size guaranteeing, if we have a party size of 6, then either 3 people will all be friends or all be strangers, right? Ramsey numbers definitely exist based on Ramsey's theorem, but they grow exponentially fast. Exact computation is extremely difficult, so most Ramsey numbers are completely out of reach. The true growth rate remains open. The bounds between these, for R of k, between those 2 numbers has been barely improved, but there's still room to go. And it matters because when complete disorder is impossible given enough of a sample size, then you can try to exploit certain structures and patterns or account for patterns that you might not have expected to arise. And there's applications for Ramsey type results and complexity theory and combinatorial optimization problems. That's what this field is related to. So, and I would say Ramsey's a smart guy, and whether that's in past tense or present tense, I'll leave up to you guys. And about those aliens, as I said, Erdos said that if an alien force demands to know the value of R5, and otherwise would destroy our planet, he's saying that we could figure it out. It's between 43 and 46, and if we devote all our resources to it, we could find it. But suppose instead they ask us for R of 6, which we know to be between 102 and 160. Then he says we should attempt to destroy the aliens. That's Ramsey theory for you. Thank you, guys.